So I didn't really plan for this talk, but I'm giving this talk sort of persuaded by Anton, because he thought that you learned about how do you go from a block basis to a one-year function basis, primarily starting from plane wave-like basis. But there are other approaches as well. So is there a question already? No. So without going into the details of the technicality, what I will do, I will sort of give you a flavor of this alternative method, and will show you how you can sort of construct some pretty pictures and how those pretty pictures can be used in understanding some physics. And that physical problem that I will choose is that of the high TC cuprate, because I think at least in the discussion meeting session, we had several talks on high TC cuprate, so at least you know the problem. So with that, let me start. So this is kind of a rough title of one subsection of my talk. So it's a one band modeling of hole doped high TC cuprate compounds, and what exactly I mean by that will be clear as I go along. And there is one reference, but most of the thing that I am going to show, most of the pretty pictures, they are largely unpublished. So this is the high TC phase diagram, which you all know. And is there a pointer somewhere? Yeah. So these phase diagram you all know, because in the discussion meeting session, you have this phase diagram has been shown to you many of the time. So you have at half filling some antiferromagnetic insulator. As you dope more and more hole, you have a kind of a superconductivity developing, and that has a dome-like shape. So what we are sort of concerned, this TC, which is the maximum of this dome, is called the TC max. And if you go through various high TC cuprate compound, this maximum TC is varying quite a lot. It can vary from 40 Kelvin to something like 90 Kelvin and even more. So while it's a burning question what sets this high temperature superconductivity, it is also important to know what is the role of these different materials in making this TC very different across this series, because after all we are looking for room temperature superconductor. This is the basic copper oxide plane, which is the basic structural unit of all high TC cuprate, and you can write it in a kind of a Hamiltonian, which has a 1 electron part and of course the correlation added to it. And it goes without saying, since we already see a material specific aspect in the variation in TC, this has to come from this single particle part. So what I show next is a band structure. You all know what is a band structure of a high TC cuprate, and as you can see, this is pretty complicated, this jungle of bands. And as Anton already said, no chemist would like to talk to me if I show all these bands. But there is one band, this is the Fermi energy, there is one band that basically crosses the Fermi level, and that is supposed to be the most important band, or that will form my low energy physics, because I am interested in the physics which happens close to this energy 0. So is there a way to pick up this one band out of this jungle of bands and construct some atomic like orbitals that will describe this band? That is basically the task. And here I sort of take a detour and tell you a little bit about the method that we will be using to sort of pick up this one band out of this jungle of bands. So let me go a little bit from the basic. What is the problem? What is the one electron problem that you are solving? It's basically very simple. You have a periodic arrangement of atoms or ions. As a result, you have a periodic potential, and density functional theory taught us how to set up this periodic potential starting from the very basic in an ab initio way. But still the question remains, this Kohn-Sham wave function, we need a basis to sort of expand those Kohn-Sham wave function. One popular basis among the chemists are the Gaussian basis, and for which Pople got the Nobel Prize, shared the Nobel Prize with Walter Kohn. The other possible basis set are the plane waves, very delocalized and very localized, two very extreme point of view. But one can take an intermediate point of view, which are known as muffin-tin orbitals, and where actually, as I will try to give you a flavor, is based basically on the description of this spherical harmonics, and therefore has a more chemical character. Okay, so what are the existing methods? The existing methods can be sort of very grossly divided into two sets of bases. One is the fixed basis set method. What are these fixed basis set method? These are the basis set which are fixed as I am going through my self-consistency loop and from one material to another material. What is such kind of basis set? Few of the things you already know in your textbook example, like linear combination of atomic orbitals, plane waves, Gaussian orbitals, all of them are fixed basis set method. That means if I set a basis set right at the beginning of my self-consistent cycle, they remain the same as I am evolving in the self-consistent cycle. One has to solve an eigenvalue problem like this. Advantage, first I should talk about the advantage. They are computationally very simple. Disadvantage, the basis set must be large enough to be reasonably complete, because I have to sort of expand this Kohn-Sham wave function in terms of a complete basis set. I cannot have a complete basis set until I have a good convergence, because in my computer I do not have infinite memory to store everything. The other kind of basis set, which was also introduced to you, is the partial wave-based method, where the wave function is expanded in a set of energy and potential dependent partial waves. You all know partial waves. You all have solved hydrogen atom problem. And you see now no longer my basis is fixed, it's flexible, because as I move along this self-consistency cycle, I'm basically changing my potential, changing my energy and everything. And the basis actually adapts to that. And one such example, cellular method, if you have done MSc course, there will be the first method that will be described is a cellular method. You also have augmented plane wave method that was discussed at length by Professor Blaha, and also a method where Walter Kohn was involved, Schodinger-Kohn-Rostocker method. The difficulty, one has to now solve a set of equation which has a kind of a complicated non-linear energy dependence. So you have to pay some price, nothing comes free. There are several advantages, of course. Being flexible, the basis is minimal. The partial waves apply equally well to any atom in the periodic table. Actually, coming from a plane wave basis, you have to do a lot of jugglery so that it should work well for transition metal oxide. And it offers solution of arbitrary accuracy for closed pack system. Disadvantages, computationally very heavy, primarily because of their nonlinear energy dependence. So you have heard about the linearized version of the augmented plane wave, that's LAPW. What we will be using mostly is the linearized and higher order in nth. You can make it quadratic, you can go to even higher and higher order. Nth order ionization version of this KKR kind of formalism. And these, as you can see, is rather powerful because it combines the desirable feature from both the world of the basis set. So the summary, small summary on foundation, we'll be using density functional theory, Kohn and Sham that taught us how to reduce to an effective non-interacting problem, self-consistent solution to a one electron Schodinger equation. How to do it? Matter is made from atoms. That's the point of view we take. And atoms are round. The plane wave basis, they are very easy to use but are not chemical, as you can understand. So what you do, you really use those projectors, you do processing to go from the block basis to one-year function basis. What will be the alternative approach? That use such a kind of a muffin-tin orbital basis, which right from beginning reflects the spherical symmetry, the orbital character of the constituent atoms. In this case, we will also derive one-year functions, but taking the route that we don't go through construction of block function, and from there use some criteria to generate the one-year functions. Minimal basis and chemical, and our ultimate goal is to understand, not to compute. So what are muffin tins? This is something which I don't know how many Indian students are familiar with, but all European students are familiar with. This is the dies that you use to make those muffins. And as you can see, you basically have this deep kind of spherical thing, and in between it is flat. And that is exactly what you do with your potential. So this is the potential. That is the underlying potential on which your electron moves. So you basically have this periodic potential, and in between, so it is deep and spherically symmetric, where your atoms or ions are sitting, and in between there is a variation, but that variation is kind of weak. So the approximation you make is that you sort of neglect this weak variation and make it completely flat. And that is exactly what is written here. You define some kind of a sphere within which your potential is spherically symmetric and outside is flat. Very good. So this will be a picture of a full potential, where you see you have these deep regions where the ions or cores are sitting, and in between there were certain kind of variation which is completely neglected when you make the muffin tin approximation. You replace it with some flat region, completely flat region. So how does it help me? This is kind of a one-side summary of the whole thing. So this entire method is based on some scattering theory. The spherical symmetry of the potential inside the muffin tin sphere allows us to work with spherical harmonics. So the solution of the Schrodinger equation inside the muffin tin spheres are nothing but partial waves. And the solutions outside, they are nothing but plane waves, as you have seen in the LAPW kind of method. What the LMTO or the muffin tin orbital-like methods does is to expand these plane waves in terms of spherical Neumann and Bessel function. That was the basic of your scattering theory. And the solution of the entire space is obtained by matching these two different solutions at the boundary of this muffin tin sphere. So that's the basic philosophy. But that sort of, already you can see that this partial wave depends on energy. So I land up into something which depends on energy, which of course I don't want. I mean, it's too complicated to solve. Then I have to sort of resort to some root finding algorithm because it has a non-linear energy dependence. So that's the reason we do some trick, and I honestly don't have any time to give you any details of the trick, but I will give you just few slides. So what is done is basically an expansion in energy, and you can do it by putting some energy points. These are some fixed energy points like epsilon 0, epsilon 1, epsilon 2, which are across the energy spectrum on which you want to calculate your bands. And this is the wave function with a full energy dependence, as is shown here. And you force your solution to sort of match at these particular points. And in between these points, you have a kind of a Lagrangian interpolation. So that's all you do to arrive to an energy independent description or the energy independent basis set. And by virtue of the variational principle, you can actually show that the error in the band energy due to this approximation is proportional to this epsilon 1 minus epsilon 0 square wherever. So, epsilon I is a particular energy in your spectrum, and these epsilon are the fixed points which you are fixing while doing your calculation. So, what we have done, maybe we can skip it because it talks about the improvement over the LMTO method. What is an LMTO method? If I had only 2 of this energy point, then it's an LMTO method, because in terms of the Taylor language, it means you basically match the value as well as the first derivative. But you can match second, third and higher order derivative, and that is exactly what was done in the nth order muffin tin method. And what it leads to is an energy selective, localized nature, makes this set very flexible and may be chosen as truly minimal. That is what is known as the downfolding technique. I will not even sort of venture into explaining mathematically how downfolding works. Instead, I will show you only certain examples how it works. If these bands are isolated, this set spans exactly the Hilbert space of the one-year functions, and if you orthonormalize this set, then they are the one-year functions. If your bands are overlapping with other bands, and you try to pick up only 1 or 2 bands which are overlapping with other bands and construct the one-year function corresponding to only those bands, then the corresponding NMTOs are the one-year like function. They are strictly not one-year functions, also true in the example which sort of David Vanderbilt showed. So, this method, as opposed to this kind of the one-year function coming from the block basis, they can be used for direct generation of one-year or one-year like function. So, with this very sort of brief introduction, let me go back to the IISc cuprate problem. So, these I do not have to sort of repeat. So, it basically captures the correct material dependence and therefore, the chemical reality that you can sort of use to sort of generate some Hubbard like Hamiltonian. So, how does it work? As I showed you before, so there was this jungle of bands. From that band structure, I want to pick up this single band, and the method actually surprisingly allows me to do that. I can actually pick up one band from this jungle of band. It looks very similar, except I have now decided to shift the 0 of my energy to the saddle point. So, it looks a little different to you, but it is the same band. And you can, what you get by construction of this one band is also the one-year function or one-year like function that describes this one band. But you see that this looks very much like copper x square minus y square. But it has tails, very fat tails, and these tails look like oxygen P, because this band, this one band that crosses the Fermi level is actually an anti-bonding combination of copper x square minus y square and oxygen Px and Py. That is exactly what you see here. But then come surprises. You do see these oxygen characters, these oxygen P like tails, which are basically sort of extending far away from the nearest neighbor oxygen. So, all it says that the one-year function corresponding to this one band is pretty delocalized in nature as opposed to what we normally assume. Good enough. Now, since I said that I will talk about the material trend and how do we understand that by using these pretty pictures. So, these are 2 IISc cuprate, lanthanum copper oxide and mercury barium copper oxide. They have kind of a similar feature. You have the copper oxide planes, and what you have is an apical oxygen, which is an oxygen out of this copper oxygen plane. And what is different, primary different, of course there are lanthanum which sits in between, and there are mercury and barium which sits between. But the crucial difference in the structure between the 2 compounds is there is out of plane oxygen, that is written as O4 here and also O4 here, and this distance is 2.8 angstrom for the mercury compound, and for lanthanum compound it is 2.4 angstrom. what is shown here, again you pick up this one band out of this jungle of bands, but now you do for two different compounds, for lanthanum compound and for mercury compound. And what is shown here is this pretty picture again, but now I decided to make projection. So this one is projected to copper oxide plane, and this is a projection which is in the out of plane. So xy plane is the copper oxygen plane, and the z direction is the direction which is out of the copper oxide plane. What you see if you compare mercury with lanthanum, first of all, this is much more delocalized in plane, and this guy is much more localized in plane. This person has lot of character, as you could see, as I am sticking out of the copper oxide plane, and this person is more or less closely confined to the copper oxide plane. So although it looks like, you have this one band, and if you really see the band structure of these two compounds, if you are not an educated person, it will see very similar. But when you really cook up these one-year functions corresponding to this band, they actually look very different. So what do we see? So as I explained here, you have this x square minus y square, and then you have the antibonding to the neighboring oxygen, which actually proceeds even to farther away oxygen. But what gives is this farther away character? To understand that, what we should actually see is the out of plane character. What you see here, now you see again x square minus y square, but you view it from only a certain direction. So you see only the blue lobe of this x square minus y square, which is again antibonding to the oxygen px. You don't see the other direction. Now you see this actually binds to something. This kind of shape reminds me of copper 3z square minus r square. So this is antibonding to this 3z square minus r square. You move out of the plane, it basically binds to the pz orbital of this apical oxygen, and it further binds to lanthanum d character and all that. So that means it sort of builds up a linear combination, which is a linear combination of copper 3z square, apical oxygen pz, and the lanthanum and copper s, which basically makes this blue lobe much fatter compared to the red lobe. That is copper S character, which is diffused, so you don't see it that well, but its signature you do see that it becomes much more fatter. If you go to the mercury compound, there is nothing out of plane, absolutely nothing. What you have is only the copper S, which you see as a kind of a bitten off thing because it is of the different polarity, the color is different. So you see that this lobe is not complete, it's kind of eaten away, and that is copper S is the thing which is responsible for that. Yes, the kz dispersion will be much larger because you have a three-dimensional character. Okay, so now you can write your favorite one band like model, which we are all comfortable with, and I think this morning Anton in the board showed something which just had the first term, and he has drawn this one band Hamiltonian, the one band structure considering only the first nearest neighbor hopping, but now it's much more complicated. You have second, third, and blah blah on a square lattice. So what are these terms? So the first nearest neighbor is basically, it happens via oxygen, but you no longer have oxygen sites in your description, you have only copper sites, you have forgotten about those oxygen sites and other basically chemical element in your material. So you have arriving to an effective description. So you have a nearest neighbor hopping, that's T. The next nearest neighbor hopping, which in a square lattice is a diagonal hopping, T prime, and the further nearest neighbor T double prime, and all that. And it was shown actually analytically by Ole Anderson and others that you can write T prime over T, you can define as a kind of a range parameter, and all the higher order hoppings are basically higher order in this range parameter with T double prime by T prime about half. So that means what is a nice thing, although you have so many compounds, you could actually bring out one single number, that's the range parameter, that will basically differentiate between one compound to another compound. So this entire thing was basically worked out, and what you see that these are three different IISc mathematics. What you find that the range parameter is actually inversely proportional to the energy level position of this orbital, which we are calling as copper s, but we should ideally call it as some axial orbital that takes care of the out of plane degrees of freedom. So why this range parameter is very different? This has to do with the position of this copper s or the axial orbital, because it's inversely proportional. So one can then draw a kind of a small cartoon level diagram. So you have, before any hybridization, this is the position of the copper 4s, let's say. This is the position of apical oxygen Pz, and also copper 3z square minus 1 is there. Now you switch on the hybridization, and the moment you switch on the hybridization, you will have a usual stuff like a bonding, anti-bonding, splitting. So if you have such a thing, you see that now the copper s mixes by hybridization through to this apical oxygen Pz as well as copper 3z square minus 1, and it is actually pushed farther up compared to its original position. How much it will be pushed depends on how strong is the hybridization with this apical oxygen, right? So that you can actually show is inversely proportional to the fourth power of this copper oxide to the apical oxygen distance, and for the hybridization between 3z square minus r square to apical oxygen, and this is between copper s and apical oxygen. They are all inversely proportional to this distance. So that basically tells us this distance was large in case of the mercury. So this hybridization was smaller, and as a result, the energy level position of this axial orbital was quite close to that of the pure copper s. While in case of the lanthanum, since this distance, this bond length was smaller, they could hybridize a lot, and that would basically push the position of this axial orbital quite far. Fair enough. You can actually sort of draw such a kind of a plot where you have the range parameter plotted in one axis and the copper to apical oxygen distance plotted in another axis, and you do find certain kind of correlation. And as you can see that when you reach thallium or mercury, basically it's kind of saturated. It's saturated because at that point the energy level position of your axial orbital has become same as that of the pure copper s, because you have made this distance so large they can't hybridize anymore. So that is the maximum you can reach if you are at the level of the single layer copper oxide materials. And that sort of gave rise to this kind of a semi-empirical plot, because all these R parameters were calculated for most known hole doped cuprates. So these are calculated numbers, where these are the TCs at optimal doping, which is found from the literature. So this is not a completely calculated plot. What you see basically is a kind of a correlation between this R parameter and this TC at optimal doping. What is shown here, if you see these materials, they have copper 3, copper 2. That means they are not single layer copper oxide systems. They are systems where you have 2 layer, 3 layer, etc. And the moment you have 2 layer or 3 layer, you will basically have now 3 copper x square minus y square kind of band, or 2 copper x square minus y square band. So you have to define a kind of a bonding and anti-bonding combination, or bonding, non-bonding, anti-bonding combination. And what is found that basically it corresponds only with the bonding counterpart of this band structure. Why is that? That is also kind of easy to understand if you understand the basic philosophy. So this is the plot again of this one-layer function describing this one band, what you should see for the single layer mercury, 2-layer mercury, 3-layer mercury, the bonding combination of this one-layer function. So yeah, I can't do anything more if I have made it pure copper S-like, but I still can do something more if I put 2 copper oxide planes and let these 2 copper S level interact with each other. That's your real T perpendicular in the language of this 2-layer, 3-layer thing. And depending on the strength of your T perpendicular, you do see now these blue lobes, they sort of prolongates and tries to touch each other. And by this way, you can lower the energy of this effective copper S of the bonding combination even lower. Yes, of course.
The bonding states of these 2 layers, that they are hopping with the next bonding layer, that will be the effective T perpendicular for a one-band bond.
That will be because if I take only the bonding combination, that's right, that's right. But how much they will prolong to each other and touch each other, that depends on the T per between the layers. So you go to the 3-band, you see that these sort of blue lobes has sort of extended even more and made the connection even stronger. Then you can ask the question that then why we cannot repeat it? Go on doing 4-layer, 5-layer, 6-layer, 7-layer. That will give me full room temperature high TC cuprates. But unfortunately, the phase coherence is broken the moment you want to extend beyond 5 layers. It's not possible to keep the phase coherence. So what you can do, just to show you, it depends on the strength of the out of plane hopping between the layers. So this is a one-layer function picture for the yttrium barium copper oxide, 92 Kelvin. You do see these blue lobes which are extending towards each other. You replace yttrium by a larger cation, that's lanthanum, you do see that they are no longer touching. So that means it depends very much on the interaction between these 2 layers. So this is kind of the summary. So the essential material dependence is contained in a single parameter R, and this is controlled by the energy level position of this effective copper S, which is like 6 to 9 eV depending on which compound you are talking about. And this is a hybrid between the various degrees of freedom which are basically out of plane. And it seems that the materials with larger R value sort of correlates with those with higher observed values of the optimal TC. And it holds good for multi-layers if my n is kind of less than 3 or equal to 3. And this should be a useful, we believe, should be a useful guide for material synthesis. Now, since we didn't calculate those TCs, why it is so? You can have some speculations. So, a long range parameter, a larger range of this R parameter may lead to better screening of the Coulomb repulsion, and that might be helpful for the superconductivity. As you can see from the one-layer function plots, in-layer coherence is strengthened, coupling to apical oxygen and insulating layer is weakened. And this actually, having this kind of a large T prime, actually helps in making the buckling phonon mode active. There is no basically report of static buckling phonon, but there might be dynamical buckling phonon. And large range parameter increases the diagonal hopping T prime, which suppresses the static stripe order. There were some DFT calculations on that, and that actually for lanthanum cuprate we do have this static stripe order, while for the mercury and other high TC cuprate we don't have. I mean, there were some reports with this charge density wave, but they are of different kind than this static stripe order. I have 5 minutes. In that 5 minutes, I will like to touch upon just lanthanum cuprate, and where basically you couple such kind of a one-layer function description with a DMFT calculation, and I will show you some spectrum. So, lanthanum cuprate, that is the parent compound for the hole doped cuprate as well as the parent compound for the electron doped cuprate. And the crystal structure in the hole doped side is known as the T structure, while the structure for the electron doped side is known as the T prime structure. So, what is the difference between T and T prime structure is again in the position of the apical oxygen. In case of the T structure, you see that you have this nice octahedra which are kind of stretched, but so that means you have the position of this apical oxygen which is directly lying above copper. While in case of the T prime structure, this oxygen is moved and it lies on top of the plain oxygen. So, in other words, there is actually no apical oxygen if you think of a T prime structure as far as the copper environment goes. So, there is a large change in the copper environment in moving from here to there. So, in one case you have a distorted octahedra, in this case you have basically some square planes. So, it was sort of thought, if we understand the electronic structure of lanthanum cuprate in these two different crystal structure, the parent compound without any doping, will that help us in understanding the mechanism of superconductivity or make a progress in understanding it? But there is a difficulty. The difficulty is that the lanthanum cuprate cannot be synthesized, the parent compound cannot be synthesized in the T prime structure. The moment you try to do that, it basically converts to T structure. And there is a reason for that, that if you see that basically it depends on the ionic radius at the A site. Smaller is the ionic radius, it actually stabilizes in T prime structure. Larger the one, which is only lanthanum, it is in T structure. And lanthanum is pretty close to this boundary where the transition from T prime to T actually occurs. So, there was this idea, if at the lanthanum side I put some other trivalent rare earth like yttrium, lutetium, samarium, europium, can I stabilize this T prime structure? And indeed, there were certain experimentalists, I do not think, sorry for my choice of color, it is some solid state communication paper, you can't see it, I can read it for you, and from Japan, where they managed actually to synthesize this compound in a thin film form. I can see it actually in my screen, but not in this. And what they did, they basically measured the resistivity of these compounds in two different structures, T and T prime structure. And what is surprising, you see about 4 to 5 order of magnitude difference in the resistivity in the two structure. They were very much criticized that they have a film, so there is the issue of strain, there is the issue of oxygen content, of course. So, we thought of doing some calculation. And this shows the electronic structure of T and T prime. This is for T, this is for T prime, same lanthanum cuprate, but in two different crystal symmetry. And again you pick up this one band. And this shows, what shows in the inset is the corresponding Fermi surface. You find that the Fermi surface is kind of rotated and rounded in case of the T prime structure, where is kind of more close to that of this straight kind of this 45-degree straight line that would imagine for a perfect nearest neighbor hopping on a square lattice. You calculate the corresponding one-year functions of this one band, and what is shown is for T structure and T prime structure. You see, surprisingly, the T prime structure lanthanum cuprate is very much similar to that of what we have seen actually for the mercury compound. So, by changing this structure, I made them look more like the mercury compound. And that is reflected also in the calculation of the range parameter, as well as how this hopping interaction basically drops off, very similar to that of the mercury compound. So, we sort of decided at this point to do some of the DMFT calculation, feeding in this input of this one band one-year function description. And what you see in black is the single particle density or state at T and T prime structure. you see their shape is actually, to start with, very different. This is much more, kind of particle hole symmetric. You have such a kind of thing. And this is very asymmetric with a kind of this hump that is developed coming from all the long range hopping interaction. If you now do the DMFT calculation, that point of time we didn't have the technology or the means to go to very low temperature. We had a fairly high temperature of 580 Kelvin. We decided to choose a U value, same U value for both the compounds. Well, ideally the U value should have been little smaller for this one. And what we find, this is what is shown in red, you do see that at this temperature, this solution is kind of insulating, but you do have a kind of a quasi-particle peak in case of the T prime structure. So we concluded, because it's fairly high, that the high temperature, that the coherent temperature for the T structure must be below this 580 Kelvin, because I don't see any coherent peak, while that for the T prime definitely is above 580 Kelvin. So this seems to be much more metallic than the T structure, in agreement with what we had in our trend study, that more metallic it is, it's better to have a higher TC superconductor. With that, I thank you for your attention. It's a very long day, and if I could excite you a little bit about this method, that would be nice. Thank you.
I'm just curious about your opinion on this other proposal on this material trend by a recent work by Gabi Kotliar and Cedric Weber also. They said it's not the T prime preliminary that changes from material to material, but it's the position of the orbital and the position of the apical oxygen that changes the epsilon d. And that gives a material trend that is, it's a year ago, 2 years ago.
I think it is perhaps the same thing we are saying in two different ways. First of all, it does depend on the position of this apical oxygen S. Now, if you think of it, there were actually some paper from Atsushi Fujimori, he is no longer in the audience, where they described in terms of some Madelung energy. And that is also related to the position of your apical oxygen. So I think it is basically the same effect, and you see different manifestation, and it's up to you which one you choose. But I don't think it's a different description at all.
Well, maybe I can, because I was going to ask the same question actually. So I can, we can elaborate the discussion a bit more. So, of course, these people do not contest the fact that the mercury would have a larger T prime and so on, okay? But I think their take would be that it's actually not possible, and this is more a many-body issue, to really understand the trends in TC from a single bond perspective.
Yeah.
And that you would have to include the actual value of the charge transfer energy in a three-band model description, let's say. So as you pull out the apical oxygen away from the plane, this charge transfer energy also goes down. And the question, perhaps you can capture that by some effective view of the one-band model. But I guess the question is now, what is the real cause in making mercury a better superconductor? Is it the T prime effect, say in the one-band description, or is it an effective view which is smaller? So, you know, that's an issue.
Do you allow me to then show 2 more slides, or? Because I stopped.
Well, you are the organizer.
No. Because I don't want to torture the student.
Can you respond after engagement comments? Because I want to add.
Okay. Then it becomes a discussion session, because I can show few slides.
So the point, I guess, is that this T prime should actually correlate with T star, because the TC is also governed by T perpendicular, because you are getting 3-dimensional coherence in the system. So it has to have a T perpendicular coming into it to get 3-dimensional coherence. So it should actually correlate with T star if it's helping pair.
No, but wait a second. Sorry, now this is going to become a discussion, really. If we have, in fact, I agree with you, of course, TC, but it's only it's only very weakly dependent on T perpendicular, you know, because it's a log kind of effect. So when we talk about TC, we could talk about maximal gap equivalently. I think that's
Can
okay.
I comment at least on Vijay's point? So if you take mercury compound and thallium compound, I mentioned something, one is tetragonal, another is body center tetragonal. So what you are saying that the link between different layer, that should be very different between your body center tetragonal and tetragonal, but their TC is same, 90 Kelvin.
In fact, the Kz dispersion for thallium should be much less compared to the mercury.
That's the correlation between your parameters.
But the correlation in that case is with the TC max.
No, if you plot it with respect to T star, it will be a better correlation. That's all I'm trying to say. T star at 0 total. Because
we can discuss later, but just to
Yeah, I think let's take 5 more minutes or.
yeah, just 2 more minutes.
Yeah,
I just wanted to make a point, since you talked about this 3 band going beyond 1 band. Let's take 2 more minutes and just show it. Yeah. So as Anton says, instead of 1 band, we should pick up 3 bands. Can we have the light at least off for a few minutes? So we should take 3 bands. We should as well have 2 oxygen bands. What is the one-year function you get? You get this copper x square minus y square, which is kind of a textbook-like picture. You have this nice x square minus y square and nothing else, very localized. So I agree, then your UDD is not material dependent. Now you look at the oxygen one-year function. They definitely do not look like a pure oxygen p orbital. That has lot of axial character. This I am showing for lanthanum compound. Compare it with mercury. There is nothing, almost nothing out of plane. So that means all the material dependence I talked about has now been translated to the oxygen orbitals. And that brings in the question that I also raised before. Then within a 3-band model, correct 3-band model, you should actually have a UPD, and the UPD then should be actually material dependent. Just to show you, if you do it without any UPD and all that, we did that with a cluster DMFT calculation. And what is plotted here is the superconducting pair correlation and temperature, and for lanthanum, for mercury. We do get a TC, but the trend is reversed. So I am not very sure just going to 3-band and keeping only UDD is a good idea. And I completely agree, there is a EP minus ED. We heard from Melis a detailed thing, how difficult it is to do the double counting. And when you do this double counting, actually your UPD plays a role. And if that becomes materials dependent, where you position your oxygen level, it's a big challenge. So you are replacing one problem by another problem. So with that note, I think I should quit, really.
Yeah. Okay, so let's thank the speaker once again.